and I'm excited to be here. Normally today I'd be giving an in-person or helping with an in-person tour at RTP Company. We'll be doing it virtually this year. As you might guess, this is not my office, so I'm also working from home right now. So gotten very used to the idea of virtual meetings here, and even interacting with our engineering staff through Microsoft Teams and video conferencing and that kind of thing as well. So yeah, that's been definitely an interesting experience, and I'm sure it's been an interesting experience for all of you as well. But so RTP Company. First of all, who is RTP Company? What are we? Own thermoplastic compounder with global engineering support and sales representation. And not to insult your intelligence, because I know that you can all read, but we'll talk about kind of break that down a little bit and help you understand exactly what that means. Because I think a lot of people, if they're not familiar with the industry or just learning about the industry, you can read this and you're like, I still have no idea what you do. And that's really the point of our meeting today, is to figure out what RTP does and how we can help our customers. We have about 1,600 employees globally right now, and about $700 million in sales. What I'm going to focus on here is that we are independent, okay, and that we are indeed a compounder. And we're going to add one more word into this. We are a specialty compounder. There's a lot of compounders out there. And what we'll find is a lot of compounders exist because they make a resin, a polymer, and then they want to broaden the ways that polymer can be used. So they'll start with their polymer, like polycarbonate or polypropylene, and they will put additives into this product to help use it in other areas. Well, that's what RTP Company does, but we're a little bit different. We are, as we would say, an independent specialty compounder. All right, so by compounder, we also blend those polymers with fillers and additives and modifiers. We are a material supplier, is basically what our job function is, what our place is. But the materials that we supply are something that we're not basic in any of the additives or any of the products that we supply. So we don't have any reactors. We are not making polymers. We buy the polymers, we buy the additives, and we're the experts in putting them together to create these specialty formulations, these engineered formulations. When we start talking about what these engineered formulations are, of course, we, like those competitors that are compound that makes the polymer, we try to fit as many different applications with as few materials as possible. The more materials you can the more applications you can supply into with a limited number of materials, that improves your purchasing power, it improves your lead time, it improves just the availability of the product. But we also understand that not every application is going to be a one-size-fits-all type of application. We might be able to get there with 30% glass fiber reinforced nylon, but we might have to add an extra component for abrasion resistance, or we might need to add an extra component for flame retardants, or we might have to add some tweaks for color. And that's where you get into the specialty formulations. We are creating engineered formulations, and that's what the product development group, which is what I am a part of, is what we especially does. And then we're also independent, and by our independence, we aren't owned by a parent company that makes a polymer. Talk about our parent company in just a moment, but we don't have anybody telling us what we should be using for our products. We can decide what polymers to use, which polymer fits their application requirements for temperature performance or chemical resistance or strength and stiffness or impact performance. We can pick the right polymer, we can pick the additives that we think are best, and then we're the experts in putting that together. And so then that way we can kind of become a one-stop shop for almost anything related to thermoplastic materials. So we would talk about our history a little bit. Our parent company, my paycheck doesn't say RTP company. It says Miller Waste Mills. That is our parent company, which goes back to 1923. And actually, it was started as a company that was recycling cotton, mostly cotton fibers. And the outlet for those fibers was actually, a lot of it went into, they would pack these fibers with grease and use them as bearings in the railroad industry. And then those fibers would kind of help give a little bit more stiffness to that grease pack. It would reduce the amount of grease that was needed. It would add a little bit longer life to the product that way. But eventually ball bearings were invented, and so these grease packs weren't necessary, and that's where Fiberite Corporation came in. And Fiberite primarily they started taking those fibers, and instead of using grease, they would use thermoset resins. And then, of course, the reinforcing fibers went from just the Miller Waste Mills cotton fibers, especially in moving into things like carbon and glass fibers. So you've got a thermoset product arm. Well, then in 1982, Fiberite was sold, and Fiberite exists in Winona. It isn't really called Fiberite anymore, but it's called Solvay. So if you drive on the other side of Huff Street down by the river, you'll actually see where Solvay is. That used to be a company that was connected with RTP, but Miller Waste Mills sold that company and retained the thermoplastic part of it, which is what RTP is. In 1982, we opened up our first European plant in 1995, so we've been expanding. For some reason, they don't have, when I started in 1998, obviously it should be a milestone, I would think, in RTP's experience, but they didn't think fit to put me into this part of the presentation. So. And I'm just kidding. We opened up our first plant in Asia in 2002. That was in Singapore, and then of course we've expanded into Asia as well. We've expanded a little bit beyond the thermoplastic compounds, those pellets that we'll show you in a moment, where we also have divisions that supply film, like Wyman. We have Resmart, a relationship with Resmart, which is actually pretty important because that gives us an arm to supply unfilled polymers as well. So Resmart is a distributor. So rather than just do the specialty compounds where we kind of have to be adding something to the material, we can also say, well, I think that your application requires an unfilled polymer, so you should talk to Resmart. And so having that relationship has been really beneficial because people can feel comfortable coming to us right out of the gate with their applications. And it may be an RTP company product, it may not, but we can help get them into the right product. So more sheet products, and then Euphoria is the color development. They're actually way out on the forefront of color development. They have a release every year of what they'll have been doing what the 2021 color palette will be, and they're preparing a 2022 color palette for kind of designers and people looking out what are the hot colors that are going to be coming out and combinations of colors. So more study really into almost a marketing type approach, but from a plastics perspective. And then we've continued to expand. We opened a plant in Poland in 2018, and we have other plans in place here for more expansion. So it's an exciting place to be from that perspective. When you look at our company locations, you can see we have plants around the world. We actually have 5 locations just in Winona. So that's pretty significant. We have our main plant, which we'll kind of be talking about mostly, but we have a high volume plant on the east end of town. We have a long fiber plant that's closer to Lake Winona. We have 2 other sheet plants, a cast sheet and then a extruded sheet area as well. So, and that doesn't even count some of the warehousing and things that we have around town as well. So you drive around long enough, you will see RTP company logos and trucks, and now you'll have a better idea of what in the world they're doing. One of the benefits of being an engineer at a global compounder like RTP company is you do get to see a lot of the world as well. So I've had the privilege of visiting our plant in Indiana, of course, all around Winona here. I've been in Texas. I've been to our Mexico facility. I've been to France. I've been to all of our Asia facilities as well. So it's kind of fun to be able to see the world and actually have the company pay for it as well. So it's kind of a benefit to these types of positions. So I'll talk about some other benefits of the engineering position too as we go along. This is the RTP headquarters in Winona. This is the plant that you would normally be visiting. And I'm really not quite sure how long our visit today will last. Because normally we would be starting, this is a 300,000 square foot facility. You'd be starting here and we'd be walking, kind of through this area, and then we'd be going down here to look at some machines. We'd stop at the R&D center here. We would walk through, this area all the way down over here to look at where we actually clean off some of the screws after looking at some manufacturing and packaging areas. We come back around here and get into our warehousing area, and then we see some blending equipment. And then as we come along here, we could also stop at our quality and our molding lab before stopping back up here. And a lot of the time is just walking. So this format, while it's not going to be quite as much fun as actually seeing it in person, I think it actually allows us a little bit deeper dive into kind of what we do and maybe fostering some discussion around that as well. But as you can see, it's a pretty big footprint. This is the Bud King Ice Arena down over here, and this is their outdoor ice rink. So pretty large place. So the compounding process is what we're going to really be focusing on. And so we are going to start with the raw materials. So in this case, we might be looking at raw materials. So maybe we start off with polypropylene resin, and then we add some glass fiber, and then we add a blue pigment. We might take those raw materials and put them into this blender. We'll talk a little bit about the blending process, but you have to take these materials, and get them blended together, and then dump them into a tote, and then take that tote to whatever machine. So the blending area is in a different area than the rest of the compounding. It's not necessarily in line like you see here. We have some that are, but a lot of them are a separate blending area. The next step is really the extrusion or the compounding process, where that blended material, and it's just a physical blend. So you've got glass fibers sitting next to these pellets with the pigment dust, powder all kind of spread throughout as well. We got to get that all into one product. And so that's where it drops into the extruder. And in the extruder here is kind of where the magic happens. And that's what we'll focus on here a little bit. Inside the extruder is going to be a barrel, a heated barrel, and then there's going to be a screw. And that could be a single screw extruder, which just has one screw. And this is really used for very simple formulas, not a lot of shear required, or sometimes applications or materials where you want to protect some of your additives. So maybe a glass fiber, for example, you don't want to really have a lot of strong mixing that breaks those fibers up, and then you lose some of the strength or stiffness capabilities of the material. So you could have a single screw extruder. A twin screw extruder is really our workhorse extruder, though. This is the end of kind of showing at the end of the screws and the barrel here. You can see that they are intermeshing. So because they are intermeshing, you can kind of see it here too, how they mesh together. They have to be co-rotating, not counter-rotating where they're going against each other, but if they're intermeshing, they have to be co-rotating so that they're turning the same way, so you can have them right next to each other, and that increases the amount of shear. You can also see from this overhead view a little bit better here, like this section right here, This is an element, a screw element that slides onto a splined shaft. And then you've got another element, and then you've got this element that's right here. And then you've got, this element that's right here. And so these are all, you can kind of imagine putting together your own screw to do whatever you want to do. You can, every element, some are designed more for conveying material into the extruder. Some are made for melting the polymer, focusing on, because you melt the polymer not just with the temperature of the barrel, but also the shear that these screws are putting on that polymer. The shear also adds a heat component as well. It's an energy that you're putting into that product, which is why you have to be careful that you don't heat it in a way or through the shear that breaks down the additives that you're using. And that's where the single screw comes into play in some cases. So you've got that shear component that you're moving in. Sometimes you're working on dispersing different types of mixing that we'll talk about as well with these different screw elements. So of course, you could, as an engineer, you could actually develop a different type of screw profile for every material that you make. But that would kind of make production unhappy, because then they'd have to build these screws for every single type of compound that when they switch from one compound to the next. And so we try to standardize to some certain screw profiles that get the right amount of mixing, dispersion, distribution, protecting some of those additives, getting them incorporated well. I'm not going to spend really any time on it, but we do have a couple of machines across our facilities called the co-kneaders as well. The co-kneader is a single screw extruder. It's got these pins that actually stick out from the barrel and notches here. And as it turns, it actually reciprocates back and forth. So it disperses the additives very well without a lot of extra high strain rate shear or a lot of extra shear stress. So, but it gets good dispersion, but it's good for polymers that are maybe very shear sensitive. So if we go back over to our process here, we've been looking as we go through the process, we were in the extruder. It's going to come out of that extruder almost like strands of spaghetti, where that then has to be cooled in some way. We'll take a look at some of that. Then we'll pelletize it, and then we'll classify it into a form. We'll try to take off any really fine dust or any pellets that got chopped a little bit too long that might bind up the process. So that way the pellets are nice and uniform as it goes to our customer. And that's the product then that we take to our quality group for testing to verify that it is what it's supposed to be before we ship it to our customer. So when we talk about this compounding process, we've got these additives that we're trying to get into the polymer. There's a couple of different types of mixing that we have as objectives for our process. We have dispersive mixing and we have distributive mixing. So you can think of the additives that we buy at RTP company as really agglomerates, whether they are the glass fibers might come nice. They might look very unidirectional, but they're kind of compact and almost like a staple that you have to peel these individual fibers off. Or talcs and mineral fillers come and they're compacted, with lots of these particles. We need to break those up. And part of the mixing is dispersive mixing. We want to disperse those additives in the polymer, or really we want to take the polymer and we want to get resin all the way around each of those individual particles if we can. And then we take that dispersed particle and we want to distribute it evenly throughout the resin. So we don't have, areas where we don't have any, and then we have areas where it's very highly concentrated. So just to kind of put that into perspective, one of the additives that we work with, not in my group, because I'll talk about the structural area that my group is in, but our conductive engineers utilize conductive carbon black. And this is an example of a very high structure conductive carbon black. They put that into a polymer to try to gain electrical conductivity. And not necessarily carrying a current, but dispersing or reducing static components so that it's protecting sensitive electronics and then those types of things. So you can see this is 100 nanometers on this this micrograph here of this conductive carbon black particle, and it's a very complex particle. And if we want to get polymer all the way covering, you know, this particle, it's got a lot of surface area. The smaller these additives are, and the more complex they are, the more surface area that you have to try to wet out. And so when you look at conductive carbon black, carbon black like this might have a surface area of 130 square meters just in 1 gram. So, you know, a thimbleful of material, you know, might be 130 square meters. To make a conductive product, we might need to put 20% of that conductive additive into a polymer. And so that could be the same, to give an idea on surface area too, so 34 grams of carbon black, so 34 thimblefuls, has the same area as a football field. So to make that 20% carbon black filled polypropylene product, it'd be the same as covering this football field with only 136 grams of plastic. That's about a third of a pound. And so you're talking a coffee cup full of plastic to evenly cover a football field. That gives you an idea of the amount of work that is required to get these dispersion and distribution of the additives. All right, so a pretty remarkable amount of work that has to happen as we do this. What I'm going to do is take a little bit of a look here at the process as well. So we've got some videos here. I will probably stop it at various points along the way so that we can kind of see what's going on here. But this is an example of a single screw extruder. And it's a little bit different area because of where this extruder is, but there's a mezzanine here that actually has the totes that are filling the material. So this is the hopper where there's a feeder dropping material into the extruder. Here's a control panel for that extruder. And the material would be pushed through with the single screw, you know, along in here. And you can see it coming out just like the strands of spaghetti that I kind of indicated as well, into a water bath. So as we go through this video, we'll take a look and see it go through that cooling bath, come out. And as it comes out, there's an air knife here. We'll let it go to the end. This air knife is actually blowing air on that strand. You can see it's causing some of that to drip out. And so we want that material to be pretty dry as it goes through it. It can't have it soaking wet. So that air knife will help pull some of the water off of there, and then it goes into the pelletizer, and then out of the back of the pelletizer then is where the pellets would be moving on to the next level. I'm going to move over here and make sure we mute this. So this is another view of the same extruder. We got the control panel that he's going to be looking at, and these are exhaust ports, so that if there's any fumes, it gets those up and out of there instead of filling up the room with polymer fumes. It takes the vast majority of those and gets them evacuated to a safe place. But that control panel is going to control, maybe I'll just pause it here. That control panel is going to control all of the barrel temperatures. It's going to tell you if you're out of specification on any of your control panel there. It controls how fast the screw is turning. I think from this panel, you should be able to control how fast your feeder is feeding the material into the hopper there. And then you got the screw configuration as a process parameter. You've got how this material comes out and how many holes the end of the extruder has. Those are all different things that kind of be manipulated there for the process. You can see another machine running in the background there as well. Just stopping it right here, you can just barely see material coming out into those pellets coming through. But that kind of gives you a little bit better idea of the scale then of the process here. And as we look at one more video here as it pops through, you'll be able to also see as he's inspecting that product. As we look down over here, we'll see the classifier. So the material, we don't really get a good view of the pelletizer, but the pelletizer is going to be dropping material right down over there. You can just see it at the bottom, those pellets coming out, and then they are actually conveyed, air conveyed up into this unit here. And as he touches that unit, watch his hands, you'll see that there's actually some vibrating going on. This whole table will be vibrating, and that's what's moving those pellets down through the process. So then any fines that you have that are too small get filtered through a screen, and they end up in this bag right here. And anything that doesn't fit, you can kind of see some holes here. Anything that doesn't fit through those holes is too long, and that goes to the end. And the stuff that does drop through is the right size, and that's what we get through here in the pelletizer. Now we get a good view at the end of the process of those pellets going into the bin. So that's kind of a good overview of our production process. Of course, not all of our equipment is going to be set up with, touchscreen displays. Our newer equipment all is. But we're running equipment that we've been running since the 1980s. And of course, you're replacing screws and doing maintenance on the barrels, those parts that wear out. Of course, you've got motors that are going to be turning those screws as well. So there's maintenance that has to happen on here. But a lot of our control panels here, these are setting the temperature. Again, you set the screw speed, you're monitoring the amount of amps being used or the amount of torque that's required, depending on the machine. That has a set point and then also an actual value. So and he has to record all of those things. So we can go back if there's any concern about a particular lot, or if the machine does go out of spec, all of a sudden one of these jumps up to set point of 440 degrees Fahrenheit, and all of a sudden one of these is reading 600. Okay, we got to stop the process and call maintenance and have them come and change out a heater band or something like that, depending on what the issue is. So a lot of record keeping to keep track of for both quality performance reasons and also maintenance reasons as well. So we have to carry this material throughout the plant. So one of the things that we have to be careful of during our actual walking through the plant tours is being aware of fork trucks driving around. They're driving all over the place. Maximum speed limit in the plant is 5 miles per hour, so it's pretty slow. And also I want to point out the warehousing area here. This is our back warehouse, or high volume warehouse, where all this is holding a lot of finished goods. And you can see here on all these racks, that you can't see really well, but these are all labeled and barcoded. So if I'm looking in my computer system and I want to find where we're keeping, and our raw material warehouse is kept the same way. If I want to find a particular raw material or a particular finished good, I can look it up in our system. And the labels on the boxes list the description of the product, the lot number, and then also the how much material is in there. I can go right to a particular box and know exactly what location it is through barcode readers on these different levels. It tells me what station it's in, and if it's on level 1, 2, 3, 4, or 5. So you see tall area, and we're using all of it with that process. So of course we have to handle materials in a lot of different ways. This on the right shows you an example of taking material and dropping it directly into one of our finished product containers. Sometimes we do that if we are this is called packing offline. If we don't have to do anything else with that material after it's been made, it's coming out dry, we just pack it right into there and it can go directly to the customer. Sometimes we have to go through other processes, and one of them might be a post-blending process where you take a tote like this and you take it to a different blender, same type of concept that we had early on, where the blender that we'll see come up over here. These can be used for post-blending as well. Post-blending is where, if you are making a product, let's say we're making a glass fiber reinforced material, let's say 30% glass-filled nylon. Well, you're not going to find that, or you will find that every pellet is not exactly 30% loaded glass fiber in that pellet. What you'll have is some that are, if you're blending it all and dropping it in, or you might even have feeders that drop in at different areas. Maybe you're feeding the glass fiber down here a little bit and the resin up on top, up at the earlier in the process. You know, when you do that, in both of those cases, your glass content is kind of going to do one of these throughout your run, whether it's the PID controller on the feeder for the gravimetric feeding of the glass. It's going to be trying to control to a certain process. Same thing if you've got this blended, you're going to have some areas that are a little bit more rich in glass and some that are a little less. And so by doing a post-blending process, you're taking those pellets that have less glass fiber and getting them next to those pellets that have more. So you're kind of evening out the distribution of the glass throughout, so that whatever you grab for material out of the first box is going to match whatever you're doing in the last box. Of course, if you're doing the blending, as I kind of pointed out here, with this type of, you can actually use this for raw material blending as well. You'd put the materials in here and then take it to the blender. But of course, when you do that, every time you go through that process, you've got it in a tote, you've got it then in the blender, and then you're dropping it into another tote. Every time you're transferring that from one container to another, it's another chance for some sort of contamination to take place. And so what we're going to do is take a little bit of a look at a video here of one of our pieces of equipment that's used for, this is basically, I think this is a tote washing system. You can think of it as a big dishwasher, but this is a different type of tote that is actually able to be closed on the top. And this is called for tote blending. So what happens here is we put our raw materials into this tote and maybe only fill it half to 2/3 of the way full. And then that's taken to some frames over here that actually tumble that material, tumble that whole tote. We've got some, also some taller ones here as well. But they basically lock in that whole thing, just tumbles. And so it's another way of blending materials. The nice thing about this with the tote blending process is you're not changing. You can put the raw materials in, you blend it, and you take it directly to your extruder. You don't have to go through the process of changing containers. It stays all in that one container, which can help minimize the possibility of contamination. So just kind of watch this out as he picks that up to take it to one of the other areas here. You can get a little bit of a view of of those totes if I just back the video up here a little bit. See if I can find the right spot here. Right here in the back, this frame, if you can kind of see it, is actually part of that tote blending. That's where those totes would go, and that top part just locks down. And but he's off to the extruder after that material, or actually to back to the warehouse because it's clean now, and so he's going to be getting material to put in there. So we've got all these additives, and you could get an idea of how we make our product. But you know, where do those formulas come from? Well, they come from our product development group. That's the group that I am in. Our development engineers, we have over 70 around the world when you look at the total art research and development staff. And so what's really fascinating and fun about being an engineer at RTP, as I mentioned, first of all, you got the ability to travel a little bit because we've got plants and customers all around the world. A lot of the travel that I have done has been for training some of those regional engineers that we have. But those engineers will focus on, first of all, we're product development. Okay, so we are interfacing, especially in Winona, we are doing product development. So we've got suppliers that supply the polymers, that supply the different additives, all coming normally to our facility. Now they're, you know, we're having meetings, you know, over Zoom and Microsoft Teams and WebEx. But they're promoting their products and trying to identify other materials that we can then buy. So we're interacting with our suppliers, our purchasing people, some cases our finance people as we work with some of those expenses of bringing in those raw materials. and some of the special testing that goes on, with those as well. But besides product development, where we're truly doing the development of these materials to understand what tools we have in our toolbox, we are also doing application development. So we have some locally, regionally placed engineers that are truly application development. They actually don't do the formulating, but they will listen to a customer and their application. And the customer says, hey, I want to make this widget, and this widget has to survive this temperature and this chemical, this type of chemical exposure, and has to be this strong or this stiff or this impact resistant. What material should I use? And so they will try to figure out through that process what materials we should try. And if we need to tweak something, or they need to get some additional, bounce some ideas off of other engineers, that's where the product development engineers come in. But the product development engineers also work directly with the customers as well. So we in Winona wear both the product development and application development hats. And that means that we're interfacing directly, besides the suppliers and the purchasing group, we are working with the sales force and directly with our customers, with our customer service department, with our marketing department, to be able to talk about, or help guide them as to what talking points on these materials are as we try to promote our products. So within RTP's engineering group, we get exposure to all different areas of the company, which is really great because it also provides some mobility. If a lot of engineers come in and they get their feet wet in engineering for a number of years, and then we've got engineers that have moved on into the quality engineering roles. We have people that have moved into purchasing roles. We have people that have moved into product management and general management roles. We have engineers that have moved into sales roles. So it's a great way to get exposure to all the different facets of a company. And then we also have our CAE group, which they help and assist our customers with their own design. So we don't design any parts at RTP, but we can take a customer's design. Sometimes customers have designed parts and they're very knowledgeable about how to design materials in plastic, or parts that are going to be made out of plastic, and how to design the molds. But sometimes we have people that are designing parts that are used to designing parts in metal or other materials, not as familiar with plastic and not as familiar with the injection molding process. And that's where our CAE group could step in, as well as making sure that the people maybe that are at some of our more seasoned customers that are doing their own preliminary analysis have the right data to plug into their analysis software, the right data for our materials. So we divide our materials up into different product groups. And so our engineering staff is divided up this way too. So I am in the structural materials group down over here, where it's kind of a catch-all for products that don't fit somewhere else. And the other areas that we have then are colors. So if you've got a product that is bringing a resin and it's colored, then you've got engineers that are focused on creating that color, matching that color. And helping promote that part of the business. You've got a conductive group where they are focused on, I talked about a little bit, electrostatic dissipation. You can imagine walking across your carpeted floor in the wintertime, and you with your socks on, and then you go and touch a doorknob, and you get that zap, right? Well, that's a static discharge. And what they're trying to do is have a very controlled static discharge. You need it to discharge, but you need to do it safely, not all in milliseconds, but over a longer period of time. And so that's some of what they are doing, is protecting usually sensitive electronics and things with materials that have some of that conductivity built in. Some of our materials are inherently flame retardant. Some of the high temperature materials are, but a lot of our materials would burn naturally. And so what they would do is our flame retardant engineers have additives that they put into materials to help reduce the spread of flame, reduce the amount of smoke that is generated, or stop that flame, extinguish that flame without letting it propagate. And then we have a TPE group that focuses on softer touch materials. So it might be the grips on the bike that you see here, or ATV, or snowmobiles. They also, you can think of anything that's soft touch. I mean, you can't pick up a pen or a toothbrush these days without having some sort of soft touch material, on that product, and that's where the elastomer materials are coming from. Structural, as I kind of mentioned, is kind of a catch-all for the stuff that isn't fit in the other areas. So a lot of it is reinforced materials, so glass fiber reinforcement, carbon fiber reinforcement. But we could also be adding materials, additives that'll help protect properties when you have very high heat exposures or UV exposures, things like that. And then you've got the wear group, which would talk about materials for anytime you have sliding or moving parts. So you're thinking gears and bushings and bearings. They're putting additives into the polymers that'll help with reduce that friction between two parts, make them slide more easily, maybe protect the surface if it's an abrasive environment. They can help protect the surface so it can, don't have material abraded away, or it keeps it looking nice for longer. Then we have two groups that are kind of focused on that sheet and film area that are kind of out of the scope of what we'll talk about today. But those are some of the businesses that we added over the years, where they're taking, in some cases, some of our compounds and then making them into sheet. So, as we, look at these different materials, we have to have a lot of different tests. And so this is a look at our quality lab. And I'm going to switch back over to our control here. This is a video that we can kind of see what's happening. Oh, I'm going to make sure I get that turned off. So we're going to have some conductive testing going on down here. He's going to be doing a volume resistivity test, where you're actually looking at how much resistance, electrical resistance, goes through this bar. You can see the ends of the bar, might be able to see the ends of the bar kind of abraded, and there's a silver paint applied. So you're not testing the conductivity across the surface, but actually through the volume of the material. Similar test, but then looking specifically at the surface, is this guarded ring test, which is measuring surface resistivity. Valdemar in the back here is using a melt flow tester, which is testing the viscosity of the material. Pam over here is also doing similar to the melt flow index test is this test that does rheology, but with its capillary rheology. So there's a little piston that spins in there to add a shear component, whereas the piston in a melt flow indexer like this unit here doesn't spin, it just is a plunger that pushes down. We have a couple of other items here. So here in this picture, Brent is using a static decay tester. This is the conductive test that is measuring how slowly, making sure that the static is decayed over the correct amount of time. Not too fast, not too slow. There's a certain range there that needs to meet. So I put it in that chamber, and you can, and it's at a certain humidity. That's why it's enclosed there. There's a certain temperature and humidity that it needs to operate at. And so that's why you're in there with those gloves on. This shows where do we do some specific gravity testing here as well. This is the rheology equipment that we kind of talked about. We also do some ash testing. There's some furnaces in the background where we burn off that resin, and we use these scales to measure. That's how we tell if a material is, it does actually have the 20% or 30% glass fiber that it's supposed to, because you can burn the resin off and then it leaves the glass fiber, keeps that from burning off. Then we have our mechanical test room as well, where we do some impact testing. Just in the back corner here, you can kind of see an impact tester. What Ray is doing here is he's working with one of our robots that does some of our mechanical testing. So a lot of our testing is flexural and tensile testing. So we're looking at how strong the material is. Tensile testing would be pulling on it, and then have to use the dog bone shaped specimen to pull on it and see how strong it is. And then the flex testing, which is what he's got right there, is like a bending test. And there you're really focusing on stiffness. So this is kind of a better view of that whole process. And here, this is our robot. And there's actually two different tests that it runs here. First of all, it's got a flexural testing section, which is right here. There's the bar right there, and this is getting pushing down on that bar, and it's measuring how much deflection there is and how much load is being pushed back up into the load cell here. So that's the flexural test. And then right here is the tensile test. And so this side will pull back away from the stationary side and put that stress on that bar. And we'll see, how it stretches, how strong it is, how much load it can take before that breaks. What's really neat about this whole system is that this robot is really assisting one of our operators. In the case that we saw earlier, it was Ray on there. This is handling the testing for both of these units. So here we can see tensile bars that are ready to go. Each blue bar that you have there is actually a bar-coded bar. So, and then right here is flex bars that are ready to go. So the robot will come over, grab a blue bar, scan it, and the computer then tells it, okay, this is a tensile test, and the next bar you grab in the next station is going to be the first bar in this test. And you've got 3 bars in this test, and it's got to go over to this station over here for testing. So it grabs it scans it, gets rid of that scanning bar, grabs the next one, scans it, because each bar is labeled with, so we understand, how it, what it's got on there too, and then it is measured its dimensions right here. So we know the depth and the thickness of width and thickness of each bar. That goes into the stress calculations that is applied after you understand what the load is. Once the measurement is done, once the test is done, it pushes that bar out of the way and puts it in the right spot where the machine grabs it and then continues its test. And this is work that one person used to do all of this work. And all of the impact testing. They had to label all the bars, get all the bars measured. And then, so of course, if they're doing a tensile test and the flexural bar breaks while they're getting this set up, well, they got to go over and set this one up, and then they might be doing impact testing. You could imagine there's always going to be a delay on some of these, because you're in the middle of one thing over here when something is done over there. And there's only so much room in this area. You can't have people at every station because it's too congested. So this robot, while it didn't replace any people, it actually allowed us to streamline that person's job. So they still go through and do the paperwork on getting the bars set up, making sure they're on the right stations, but then they can go and do their impact testing while the machine runs all the rest of the mechanical tests. And so really streamlined, and this was a bottleneck area. Materials would get done, but you're waiting for that test results. Since we put that robot in, that really streamlined that whole process. And then finally, just to wrap up, you can imagine, or you might wonder too, where all of these materials go. Well, with the different types of products we have, you can imagine that goes into lots of different areas. And here you can see that it does. We supply material. Our largest area is the automotive area. Probably 20 to maybe 25% of our business is automotive, and that's an area that's struggling right now. But the nice thing is that we are really otherwise diversified in the types of applications that we supply, because we do a lot in the medical industry, which of course now that's a really popular area as you're in the middle of a pandemic. We supply a lot of materials into electronics packaging and data storage, and of course with technology and also electronics material applications as well, disk drive components and computer components and housings. So as you can imagine, that's always a growing area. Energy has, from oil specific energy to wind and solar as well. industrial parts, aerospace and defense, sports and leisure. I mean, you name it, we supply materials there. So that really helps make it a very diverse job function as well, because as a structural engineer, I work with the medical, I work with automotive, I work with agricultural and non-automotive transportation. I assist in some of the aerospace and defense stuff. I've done a lot of sports and leisure things, just a lot of variety with the different types of applications that we get to work on. So, but that pretty much finishes my presentation and my tour of RTP. I hope that you enjoyed it, and am certainly happy to address any questions that you might have.
Okay, thank you very much, Carl, for the very interesting talk. We learned a lot. In fact, I should tell a student this was much more thorough and closer look compared to the regular tours we had. And you nicely explained everything. Maybe if they don't have question, I have a question for you. Are you hiring anybody, any summer intern, something to help the student apply to?
Yeah, most years we do have some internships available. We're currently not hiring anybody right now, and we don't know what the spring is going to look like, just because of, you know, the business environment right now is a little uncertain and stuff. So right now we don't have any specific plans, but certainly keep your eyes open. You know, if you're in the market for engineering positions, you know, as we hopefully this, you know, starts to loosen up here a little bit as we get, you know, through the flu season and into the spring. But if anybody has a crystal ball that knows exactly what's going to happen, you know, let me know.
Right.
I'd love to figure that out. But we do have, generally we have interns both in our quality area and a few interns in our engineering area, and they do various things from testing to actually running some of our products, helping with the development there. And so when we have those opportunities available, they're good opportunities. We just don't have any right now.
Any question? So once you start blending the polymer and the glass fiber, the size of fiber is about 1/8 of inch or 1/4 of inch?
Yeah, so the pellets are probably about 1/8 of an inch in length when we finish our product. Right. Most our general products. The right. Fibers going into it are probably a little bit longer than that. They're probably anywhere from 10 to 13 microns in diameter. But then the length is usually 3/16 of an inch to maybe 1/4 of an inch in length. But of course, it's a shear intensive process, and so those fibers are breaking down, you know, as a part of that process.
So the average fiber